Welcome to this comprehensive guide on torch.nn.Linear. Today we're going to master one of the most fundamental building blocks of neural networks, the linear layer. We'll explore its architecture, understand the mathematics behind it, learn how to work with multi-dimensional inputs from 2D all the way to 4D and beyond, and see how to apply linear layers in practical scenarios. By the end of this tutorial, you'll have a deep understanding of all the parameters and best practices for using linear layers effectively. Let's start by importing all the libraries we'll need for this tutorial. We're importing Pytorch and its neural network module, NumPy for numerical operations, and Matplotlib with Seaborn for creating beautiful visualizations. I'm also setting a random seed to ensure our results are reproducible. Perfect! We've set up our environment with a Seaborn style for clean visualizations and initialized our random seed for reproducibility. Now let's dive into the architecture overview of the linear layer. The linear layer implements what we call an affine transformation, which is the fundamental building block of neural networks. If you look at the diagram, you can see how the input flows through the weight matrix and bias to produce the output. The mathematical formula is y equals x w transpose plus b, where x is our input tensor, w is the weight matrix with dimensions outfeatures by infeatures, b is the bias vector with outfeatures dimensions, and y is our output tensor. This simple formula powers much of deep learning. Here's something really important to understand about linear layers. They're not limited to just 2D inputs like many people think. Linear layers can actually work with any number of dimensions. Whether you have 2D batch inputs, 3D sequence data for transformers, 4D image patches, or even higher dimensional tensors, the linear layer handles them all seamlessly. The key insight is that it always operates on the last dimension while preserving all other dimensions. Let's look at the basic example, which is the simplest usage of a linear layer. Here we're creating a simple linear layer that transforms 10 input features to 5 output features. I'll create a batch of 32 samples, each with 10 features, and pass it through the layer. Let's verify that the shapes work as expected. Great, you can see the input shape is 32 by 10, representing our batch of 32 samples with 10 features each. The output shape is 32 by 5, showing that each sample now has 5 features. Notice how the weight matrix has shape 5 by 10, which might seem backwards at first, but remember we transpose it during the computation. The bias is simply a vector of length 5. Now let's verify that the linear layer is actually performing the mathematical operation we described earlier. I'll manually compute the output using matrix multiplication and bias addition, and check if it matches what the linear layer produces. Excellent, we've verified that the linear layer indeed implements y equals x w transpose plus b. The manual computation matches the layer's output perfectly. Let's explore all the parameters that the linear layer accepts. We have infeatures and outfeatures which are required and determine the dimensions. The bias parameter, which defaults to true, controls whether we learn an additive bias term. The device parameter lets us specify whether to use CPU or CUDA for computation. And the dtype parameter sets the precision, with float 32 being the default. Each of these parameters has specific effects on how the layer behaves and performs. Now let's explore these parameters in detail. Let's explore how the infeatures and outfeatures parameters affect the layer. I'll create layers of different sizes to show how the number of parameters scales. A small layer with 5 inputs and 3 outputs, a medium one with 100 inputs and 50 outputs, and a large one with 1,000 inputs and 500 outputs. Look at how the parameter count grows. The small layer has just 18 parameters, the medium one has about 5,000, and the large layer has 500,000 parameters. This quadratic growth is why model size can explode quickly in deep networks. Now let's examine the bias parameter. I'll create 2 linear layers, one with bias and one without, to show the difference. With bias enabled, we have 50 weight parameters plus 5 bias parameters for a total of 55. Without bias, we only have the 50 weight parameters. Notice that when bias is set to false, the bias attribute is none rather than a 0 tensor. Let's visualize how Pytorch initializes the parameters of a linear layer. By default, both weights and biases are initialized uniformly within a range determined by the input dimension. Looking at the histograms, you can see both the weights and biases are initialized uniformly between the red dashed lines. These bounds are calculated as plus or minus the square root of k, where k is 1 over the square root of the number of input features. This initialization helps with gradient flow in deep networks. Now let's explore the d-type parameter, which controls the precision of our computations. We'll test float 32, float 64, and float 16 to see the memory implications. As you can see, float 32 uses 4 bytes per parameter, float 64 uses 8 bytes for higher precision, and float 16 uses just 2 bytes, which can speed up training but may reduce accuracy. The choice depends on your precision requirements and memory constraints. Now let's explore one of the most powerful features of linear layers, their ability to handle multi-dimensional inputs. Starting with the standard 2D case, we have a batch dimension and a feature dimension. The linear layer transforms the feature dimension while preserving the batch dimension. Perfect, our 2D input with shape 32 by 10 is transformed to 32 by 20. The batch dimension of 32 is preserved, while the feature dimension changes from 10 to 20. Now let's work with 3D input, which is common in sequence processing models like RNNs and transformers. Here we have batch, sequence, and feature dimensions. Excellent, the 3D input with shape 32 by 50 by 10 becomes 32 by 50 by 20. Notice how both the batch dimension 32 and sequence length 50 are preserved, while only the feature dimension changes from 10 to 20. This is perfect for processing sequences where you want to transform features at each time step. Let's try 4D input, which might represent image patches or spatial feature maps. We have batch, height, width, and feature dimensions. The 4D input with shape 32 by 28 by 28 by 10 transforms to 32 by 28 by 28 by 20. All spatial dimensions are preserved, only the feature dimension changes. This is incredibly useful for patch-based image processing or when working with convolutional feature maps. And linear layers even work with 5D and higher dimensional inputs. Let's test a 5D tensor with batch, depth, height, width, and feature dimensions. Amazing! The 5D input with shape 2 by 4 by 8 by 16 by 10 transforms to 2 by 4 by 8 by 16 by 20. Linear layers really do work with any number of dimensions, always operating on the last dimension while preserving all others. Let's visualize how linear layers process multi-dimensional data by looking at the distribution of values before and after transformation across different input dimensions. This visualization shows how the linear layer preserves all dimensions except the last one. Whether your input is 2D, 3D, or 4D, the transformation applies consistently to the final dimension. You can see from the histograms how the input distribution in blue is transformed to the output distribution in red, with the transformation being consistent regardless of the input dimensionality. Now let's explore gradient flow and training dynamics with linear layers. Let's demonstrate how gradients are computed through a linear layer. I'll check the initial gradient state, perform a forward pass, compute a simple loss, and then run backpropagation. Perfect. After backpropagation, we can see that gradients have been computed for both weights and biases. The gradient shapes match the parameter shapes exactly, and we can see the gradient norms, which give us an idea of the gradient magnitudes. This is essential for understanding how the layer will update during training. Now let's visualize the training dynamics of linear layers in a simple neural network. I'll create a 2-layer network and train it on a regression task, tracking the loss, weight norms, and gradient norms over time. Excellent visualization of training dynamics. You can see the loss decreasing smoothly on the left, indicating successful learning. The weight norm in the middle shows how the weights evolve during training, starting small and growing as the model learns. The gradient norm on the right shows the magnitude of updates at each step. The training was successful, reducing the loss significantly. Let's see a practical application by building a simple multi-layer perceptron. Here I'm creating an MLP class that chains together multiple linear layers with RayLU activations. This architecture takes 784 input features, which could be a flattened 28 by 28 MNIST image, passes through hidden layers of sizes 256, 128, and 64, and outputs 10 classes. Let's test it with a batch of 64 flattened images. Our MLP is working perfectly. The architecture transforms 784 input features through hidden layers of 256, 128, and 64 neurons, finally outputting 10 classes. The total parameter count is about 243,000, which shows how parameters add up across multiple layers. Let's visualize the architecture of our MLP to better understand the layer sizes and how information flows through the network. This bar chart beautifully shows the architecture of our MLP. Starting with 784 input features from a flattened image, we progressively reduce dimensionality through hidden layers of 256, 128, and 64 neurons before reaching our final 10 output classes. This funnel-like architecture is common in classification networks. Now let's explore some advanced usage patterns, including custom initialization and weight sharing. Let's apply custom weight initialization using Xavier Uniform Initialization for the weights and zeros for the bias. This is often better than the default initialization for deep networks. After Xavier initialization, we can see the weights have a mean very close to 0 and a standard deviation of about 0.11. The distribution is uniform between about -0.2 and +0.2, which helps with gradient flow in deep networks. Now let's demonstrate selective freezing, where we freeze the weights but keep the bias trainable. This is useful for transfer learning or when you want to fine-tune only certain parameters. Perfect, we've successfully frozen the weights while keeping the bias trainable. After backpropagation, the frozen weights have no gradient while the bias does have a gradient. This selective freezing is a powerful technique for transfer learning. Let's compare different weight initialization strategies to see how they affect the initial weight distribution. We'll look at the default uniform initialization, Xavier uniform and normal, and Keiming uniform and normal. This comparison shows how different initialization methods create different weight distributions. The default uniform initialization creates a flat distribution. Xavier methods create distributions suited for linear activations, with the normal variant being Gaussian. Keiming methods are designed for RayLU activations, with slightly different variance calculations. The choice of initialization can significantly impact training dynamics, especially in deep networks. Let's summarize the key takeaways and best practices for using linear layers. First, remember that linear layers support multi-dimensional inputs of any dimensionality. Not just 2D, the operations always apply to the last dimension while preserving all others. The weight shape is always out features by in features, and remember the transpose in the computation. Initialization matters, especially for deep networks, so consider Xavier or Keiming initialization. And when using batch normalization, you can set bias to false since batch norm handles the bias. Common patterns include using linear layers for classification heads, dimensionality reduction, feature expansion, and sequence processing. For performance, remember that matrix multiplication is highly optimized. Batch processing is more efficient than individual samples, GPU acceleration works automatically, and mixed precision training can speed things up significantly. Let's finish with a comprehensive example that shows how linear layers work flexibly with various input dimensions. I'll create a model that can handle 2D, 3D, and 4D inputs seamlessly, demonstrating the true flexibility of linear layers. Perfect! Our flexible model successfully handles 2D batch inputs, 3D sequence inputs, and 4D spatial inputs, all with the same linear layers. The model correctly preserves all dimensions except the last one, transforming the feature dimension from 10 to 5 in all cases. Congratulations, you've now mastered torch.nn.Linear.